Okay, so the order of the presentations will be random, and we will do the draw live right now. Okay. Yeah, there are 28 groups. Okay. So first group is group 8, then group 1, group 3, 5, 6, 2, 7, 4. Okay. Uh, Okay, so the first group is going to be group 8, and the topic was auto distribution and safe fallback in LLM agents. So when you are ready.
We need to talk in a microphone, right?
Yes.
Yeah, okay.
You have a microphone. Please don't forget to, when you are going to talk, to come here. Also, remember we have 10 minutes per presentation, and since we are in a tight timer, please try to adjust to that time, okay? You will have a timer here.
Okay. It's not connected to this computer, but I can switch if you want. We can change it.
May I start?
Yes.
Good morning, everyone. We're Group 8, and our presentation is about auto distribution and safe fallback in LLM agents. So first of all, why do we care about auto distribution? We care about OOD because when we're in this OOD scenario, it means that our agent is on unfamiliar ground and unexpected things could happen. So maybe a misunderstanding of the task could lead to a bigger issue, or a small issue could propagate and becomes a systemic problem and pose a threat to the system and to the user. So for some definitions, in the traditional machine learning sense, we define auto distribution as a distributional shift in the training data. But when we're speaking about agentic AI, it becomes a bit more complicated to define what is this distribution. So we propose the use of the term called out of scope. And we propose defining out of scope as anything that's outside the operational realm or the intended use of that agent. And in order to define the scope of the agent, we thought about tackling across two different dimensions. The empirical one, which would be a set of input questions or intended tasks that the agent can perform. So let's say it's an agent in the healthcare domain. These would be questions that the agent is designed to help with. And the semantic dimension, which would be the set of system prompts and the constitution of this agent, which would define how it operates.
Now, how we do actually detect OD? One of the main approaches is predictive uncertainty. But we argue here
and we cite this paper from the last year, that they say that OD and uncertainty and completely disalignment if we don't take care the following. A classifier is trained just to determine which class belongs to each query, right? Why this should be a good approach to detect OD. And these two examples explain it properly. Let's say that first of all we have an in-domain sample, but a really hard sample. You know, we always have these samples in datasets. We have here a cat that might be also a dog, or I don't know what it is, and neither the model. So the uncertainty, the entropy of the distribution of the probabilities might be high, while it is in scope or in distribution. In the second sample, we are sending a query with a plane, okay? And we cannot expect what the model should behave in that case, because maybe the model just determined whether it's a cat or not, right? And it didn't learn nothing about dogs. So this is an out-of-scope sample where the uncertainty might be high. So how do we solve this if we want to use uncertainty to detect OD? So we need a signal. And in order to have this signal, we will explicitly train a scope classifier. A scope classifier is just a binary classifier that determines whether a query is in scope of the agent or not. First, we need to define the scope, and then we can train this. This is very important because this classifier is completely independent from the LLM, so it cannot inherit the overconfidence of the LLM. Now, can we really trust this classifier? Because it might be wrong, right? It's just another machine learning model. So, no, that's the answer. And one of the limitations of these binary probabilistic models is that a single probabilistic model doesn't know how to say, I don't know. Why? Because we are forcing models to make precise prediction, to choose the probability, right? But we don't know nothing about how uncertain is the model about those probabilities, you know? This example that we have here show it. For example, a binary model will predict this uniform distribution over this image over here, where we have both features from a dog and a cat. We have the same evidence to each classes, and the same situation will occur if we send just a random image. But these situations are completely different. In the first one, we have all the information available, and in the second one, it's just noise. It's just lack of knowledge, and both are represented in the same way. You know, this is ignorance and indifference are represented in the same way. I cannot see the timer. Yeah. So how would you avoid this? How can we differentiate between these? We are opting for some imprecise probabilistic classifier by a Credal set. What is a Credal set? I will not go into the technical details. You can ask me later. But a Credal set is a convex set of probabilities. I will just show as a view, because in the binary case, this is just represented as an interval. Each probability in this interval, it's representing somehow a plausible probability distribution. So in this way, we let the model to not only express the probability, but how uncertain it is about those probabilities. Here, the uncertainty about the ground truth probability is high, the width of the interval is high, and in the other case is low. And how can we use this to actually have a robust classifier that determines whether the query is in or out of scope and which decision we do take? So we are taking the action based on epistemic uncertainty, which is this ignorance that I mentioned before, right? So let's go to the first case. We will have two thresholds, one for low uncertainty and the other one for high uncertainty. And when the model is fully certain about his answer, when this Credal set, the width of the Credal set is low, we will both take the action if the query is in scope, or abstain if the query is out of scope. Now, what happens when the model, the scope classifier is not fully sure about the answer? There is some uncertainty there, right? So in this case, we will ask for more clarification or a specification for the user. And in the extreme case, when there is completely lack of knowledge, the model doesn't have a clue of what's going on, then we abstain of answering and escalate to human. This is the framework based on some decision that we consider in this work. These thresholds can be optimized, chosen, like there are different ways. This is just the proposal, of course. Yeah.
And here we present a high-level classifier would take part in agentic system. So it would be a layer in between the user and our agentic system. And here is where we would have the LLMs and the tools. And then depending on what was classified as for clarification, proceed or abstain, we would, the system would react in a different way. So evaluation metrics for our scope classifier, we would have our traditional accuracy, recall, precision, depending on the for the 3 labels that we have. And then we would have the area under the accuracy and rejection curve, which is a plot of the accuracy of the model versus the rejection rate. This is just not from our experiment or anything, it's to illustrate based on this paper's definition. And it helps to test whether the selective rejection improves the overall reliability and if we're correctly capturing the trend of the epistemic uncertainty in our classifier. We would like to finalize our presentation talking about governance and accountability. So how can we translate our ideas into something more plausible and contribute to the field of responsible AI? We understand that it's very hard to design, develop, and deploy safe agents. So what we thought about proposing, and maybe that could help, is it's a protocol for deploying agents that are robust to out-of-scope scenarios. So here we present a checklist of what developers and institutions and companies should think about when designing those agents. So it's very important to always well-define the scope. Well-define the scope of the agent. It's important to design and develop these out-of-scope detectors in the agentic pipeline. It's important to think about the escalation mechanisms that this agent might have. It will all depend on the different scenarios, budgets, and etc. It's also very important to monitor inputs, outputs, tool logs, any errors. This agent must go under resilience testing, so stress tested and make sure that all the fallback mechanisms are working, and incident auditability. So if something goes wrong in production because we can't anticipate everything, are we able to trace back this example and try to reproduce it? And we hope that this proposed idea could support institution and governmental oversight, as well as designing future regulatory standards for robust and safe agents. Thank you very much.
One question? There's a microphone. Yeah.
Thank you. It's perfect time. Thank you very much. One question is fundamental to have a good classifier, as you said. Have you in mind how to create the data set with the query or the prompt in order to organize the...
Yeah, so indeed, thank you, Paco, for the question. This is one of the main, we will say, limitations of this proposal, because how to define this scope, like the idea is clear, but how to define it actually is not trivial, because you enter in the trade-off between how much resources do you take to do it in an empirical way, or how this kind of robustness that you might lose due to the semantic definition of the scope, right? But we believe that thanks to how we define the model, and we don't want the best classifier, but we let the classifier to say, I don't know, in the sense that even the classifier is not the best one, we don't have many samples and the best data set, we might end up in the situation where the classifier says, honestly, I don't know. And in that case, we will abstain from answering to protect the user from that. So we don't believe it's a huge problem, right? Of course, the ideal situation will be to always have confident answers, but we believe that this in machine learning is never a possibility.
We also think in terms, if we're speaking about a product, to create a data set is very challenging, but we could always go through an alpha phase where we select a pool of users and then with time monitor how they're using, and based on these initial interactions build a starting data set for the classifier.
Okay, thank you. Congratulations. I like the idea, and it is very interesting. Thanks.
Thank you.
Well, derived, very good presentation, by the way, and derived from the Paco's question, I was also wondering about the thresholds that are, from my point of view, you referred that they could be fixed manually or some kind of optimization process. Have you, I mean, it is not easier to fix them, but what about the consequence of bad alignment of these thresholds?
Sure. This is something important. We are relying on some thresholds to determine whether we take an action or other. What we believe is that we have to be optimistic with this threshold in order to prevent that, because let's say what will happen if something that we are fully sure about this, but instead we are in the second step, right? So the worst case here is that we are asking more clarification from the user. It's not even LLM inference, so we are not taking that much resources and just asking the user to clarify it. The same happens with the high threshold. Here, is it true that if we are very pessimistic, we will be escalating to a human many times, and this might be a drawback depending on the context. But in order to, we could use this metric that we said before. We will always have a trade-off between this, no? So it will be context dependent, but we believe that we should be pessimistic, because the worst case is, like, we should ensure that if we answer it's because we are really confident, no? So this tau1 threshold is the most important one, and if we are pessimistic there, the worst case should be asking more over clarifications. So yeah.
And thinking in an example scenario, and I think it would be great if we could bring an expert in the domain to help with this threshold calibration, because let's say we're building healthcare agents to help patients with diabetes to measure their insulin levels, let them know when they have to take the medications or what they should do. And let's say we get into a blurry scenario, right? Should the patient asks the agent, can I increase my dosage? Maybe the agent has some context about it can increase in the dosage in specific scenarios, but it might be blurry. And I think that's when human intervention becomes critical to in those scenarios, decide whether to abstain or not. And then based on this human in the loop from the expert, we can better design these threshold values.
Okay, thank you. Thank you very much.
Thank you.
Group number 1, please come here.
Bueno, vamos rápido. Vamos a hacer una pregunta por una pregunta y 5 minutos. Y respondemos. Cambio el título.
Yo solamente puedo pasar para no tener que pasar, no...
Y apunta los títulos y todo.
Okay, so now we are having group number 1, the first of the 2 groups about explainability in agentic AI systems. So whenever you want, you can.
Let's wait to timer, right? Yeah, no, I'm waiting to timer a bit because. Okay. Well, good morning, everyone. We have Group 1 composed by Hamed, Jaimara, Alvaro, Christian, myself, and Fabrizio that could not be here today. Our proposal is trace ground explainability for clinical agentic systems based on the clinical trace explanation packet. Our main argument is that in agentic systems, especially in the healthcare domain, the final answer is need to be explainable, but not only the final answer, also all the process behind it. Also, the explanation must be adjusted to a specific stakeholder. So we say that one trace can have multiple views. Now, why that matter?
Well, thanks, Nico. In the past, the explainability is only focus of final output. Well, for example, in the classification tags, we ask an explainability try to answer the question why the model offer the class A and not the other class. Or, for example, in segmentation tags, try to why this part of the image is more relevant or more important to the other. At the moment, and the present, in agentic system, they are complex because we no only have one answer. We need to understand all the steps of the model, try to identify the final answer. But we have a little problem. In the real time, all the model, all the agentic system, have hidden the step of this opera. We maybe in agentic system we have planning, evidence retrieval, and different external tools to elaborate the final output. So in a healthcare, it's very difficult and it's very important to understand all the steps of the model tried to elaborate the final answer. So we have identified different challenges, different problems. The first is the trace completely. We not only need the answer. We need all fundamental. For example, we need the information of the output of the different tool. Maybe we use a model to classify the user information. We need after faithful trace. We need to understand all the steps of the output because we have a different stakeholder and need to explain the information for everyone. Previously aware, we create a same trace with all information, but we need to reduce this information and determine which is most important to every user. For example, in a clinician, we don't need be careful, friendly response. We need more detail of the answer. The fourth is the evaluation gap. We have to determine how to evaluate the problem and how to evaluate the answer is correct. Not only apparent is good, we need to determine with a fundamental and base to offer the answer. Now, Nico, we are explaining the proposal.
Yeah, let me short the clinical trace explainability packet by CTIP because it's too long. So the CTIP is not only a natural language explanation. It is a structured data that is based in 3 pillars. First is trace grounded. That is around all the agentic workflow. It tracks which agents, with decisions, tools, why that decision and not another, and so on. Second, it is stakeholder aware. Why? Because you are not going to give to a nurse or a doctor or a clinician or even a regulator, if it is needed, the same explanation. You need to adjust the explanation to the stakeholder. And third, it is faithfulness tested, because we have a trace where we can check if the agentic workflow is doing what supposedly it is doing. So with this, we are moving explainability from just the final answer to all the process behind it. Now, how can we insert our proposal into a plausible clinical agentic workflow? Yeah, at the top we have the stakeholder. The stakeholder will do a request to the agentic system. The request is processed by the planner, where the planner will do now the orchestration with each agent. The agent can be a data agent, an expert agent, and so on. Each agent will have their own tools that can be a clinical imaging, medical history, medical databases, patient sensors, for example. While the agentic workflow is doing their work, we will be keeping the track of everything what it's doing. So we are building our CTEP online. Now, when this pack will be passed to explaining agent, the explaining agent then will adjust the tailored explanation to the stakeholder. Finally, on all this loop, we have a completely human oversight where the stakeholder can do any change or request it. Now, I would like to make clear that we have two actors here, the agents, all the technical parts, and the stakeholders, that are the persons who are affected by or are using the system. They interact with each other with a continuous human in the loop where we can review, clarify, correct, or escalate, for example. Now, what can we do, for example, with the trace explainability?
Well, CTP generate one trace, a lot of information, but we can use a different form or different technique to explain. The first is a verification. Verification trying to follow the different steps of the model of the different agent, elaborate the result, and use the information. Okay. The second is the attention. The attention is highlight the trace segment or more important to the response, the final response, the final output. And the third is the counterfactual. Counterfactual is usually used in time series. It tries to answer the question what need to change of the output or on the, in the input to change the results. And in this case, we can change, remove a tool, remove some information, and maybe the output change. When again, we have one trace and multiple view, because we need to convert all the information and try to reinforce the explainability of the different users. For example, the clinical view is different of the patient view. In clinical need more detail, maybe the system can suggest some step for the new proof, and however, in the patient we need more clarity. We need more implication to care. And for other example, we as regulator view, we need more expensive of the system. Can you reduce the cost of, for example, the information? We need all the information of the system, or we can reduce this. Now, Nico,
we expect approximately at least 4 contributions. The first is a shared evidence, because we are using the same evidence to do every explanation. The second, role specific, we are tailoring each explanation to the stakeholder. Second, reduce post hoc rationalization, because using the trace, we are preventing the agentic system to do a post hoc explanation, trying to justify without any empirical base. And finally, this can do a strong accountability by checking the trace. If the system is not doing what it's doing, so we can say, hey, this system, why you are not doing that? Finally, the CTEP connects execution, explanation, and governance into a single framework, or at least it's what we want. Now, what can we do in the future?
In the future, well, realmente, at the moment, we need to evaluate the different forms. The first is the faithful next checks. We need to determine the test the trace and to explain it is correct. It covers all the part. The second is, for me, is the best or the more important. We need to stakeholder review. We need to ask to different users of the system, see if the output or the answer is useful for them. 3 is the privacy aware. We need to remove the information not relevant for every user. For example, we remove the technical detail for the patient. 4 is a baseline comparison. We need to compare CTEP versus the state of art and the traditional postcode explanation. Well, oversight, defining oversight auditing. Thank you for attention. You can scan the QR for more information for the website of the project.
Thank you for the. Is it working? So thanks so much for the presentation. It's actually a very difficult project. Yeah. So I have a very difficult question because, I mean, I fully agree on the explainability framework you have provided and the idea of to reduce the post-hoc analysis and focusing on the traces. Mm-hmm. But then you add an additional problem that is the agency. So, of course, you are not going to solve it just now, but have you thought about the possible conflicts in the 4 agents you are designing? So how will you deal with the conflict resolution mechanisms in order they integrate it? Because it's all what you have already presented is a difficult problem for a single model, but when you have different agents. So some ideas about that?
Well, thank you for the question. The time of the summer school is very lowly, but this last day on the Sunday, the weekend, we elaborate a little demo, but the problem is we can't publish in the website. The first problem is we need to understand every agent is independent and is an expert of a specific task. Later we have another agent to try to evaluate the conflict of for example, in my research lab, I have a teammate with collaborate in radiomic specific, and I ask him for this problem, and I say is maybe in some problem of the breast of cancer, the image have another information with, for example, a radiomic. For example, a convolutional neural network detects some part is radiomic is output is in model. Yes. And then we need to publish this part of the evaluation because we only elaborate the full workflow, the trace, the part of the trace, because the trace is all information. It's very difficult communicate or summary all the information in part that the model don't hallucination. Well, if you
perfect, thank you.
Okay.
Okay, so group number 3. Okay. Okay, so now group number 3 will explain their proposal. Their topic is human oversight in agentic workflows in high-risk settings. Okay, so when you...
Good morning, everyone. Today I, Muhammad, and Ignacio are going to present on behalf of Group 3. Our topic today is human oversight in agentic workflows. We're going to go through the architecture, how are we going to design the system, what kind of concepts or solutions we're trying to use in order to solve this issue. Before starting, I want to ground and anchor our presentation around these three main questions: the when, the how, and the what. When should we involve human in the loop? How should these systems be designed to integrate a human in the loop? And what processes need to be, what processes a human should be involved in versus what are autonomous or auto-decided by the agent. In this diagram, we're explaining the problem. Previously, we used to have systems or programs that are static. It takes an input and it will generate an output. But now with agentic AI, we have systems that will read from multiple components and will take action on certain systems. As these systems grow, it becomes unclear and untraceable on how to figure out how these systems are talking with each other and analyzing. So it becomes like a black box issue. And it becomes harder for the human to make a decision because a lot of information is being processed. As we can see here, it starts from an LLM, and then there is tool usage, there is planning, and then there is an agent, and some autonomous actions are happening behind the scenes. It introduces automation bias, unsafe autonomy, responsibility gaps, and cognitive overload. Why is oversight hard? Here, as we used as one of our references, we drew the conclusion around Kahneman's framework, which says that the human either thinks in a slow and analytical way, or fast and which can lead to error-prone results. And usually, these agent systems will tend to push the humans towards the fast and error-prone way. And then here we have our research literature review and some of the gaps regarding accountability and when should we hand over to the agent versus the human. And here I want to hand to my colleague Ignacio. Thank you.
So, we are trying to solve a really difficult problem. We are focusing on a whole system taking real-world decisions with real-world implications, killing people, moving millions, controlling industries. So somehow we must put in place all the concepts we've been talking these days. We need a mechanism to explain, to understand, to control that. We have found lots of examples of real-world possible applications, very far away in time to real application. But on the other hand, we have found an application that we all would consider is already here. What these systems are and what are the small tricks about that? Okay, we have an agentic system that must take decisions in the real world with real sensors. Your feeling of the world must be specific, concrete. We're somehow using a world model to take all these decisions. But if we need a human to certify, to approve, it's not enough to say, okay, give me yes or no. No. Give me back all the meaningful information. It's not enough. I cannot reprocess all the data again. I am not an agentic system. I am a human. So how do we concentrate all this information so that a human can make a reliable decision? And it's a problem of summarization, how to absorb this information, synthesize it, and explain it to a human in a way he can take a proper decision. think of a financial system. You could also think of a missile system, or a general trying to understand what's happening in a battle. We have lots of decision mechanisms that must be controlled, and all the problems of guardrails and supervision are in place. But on the other hand, we have Mr. Elon Musk that is simply forgetting the problem. He is considering a driverless vehicle. There will be no driver. This way, I resolve all the problems. I do not put the human in the loop. Even though he has lots of problems to solve. Think of it for a minute. First, the problem they are facing with the autonomous vehicle is a very, very simple one. An accelerator, a brake, and a steering wheel. Billions of humans drive every day, so it's not that difficult. Anyway, the control mechanism they have to put in place, safeties, forces them to forecast, to predict the behavior of all the vehicles around, of all the pedestrians around. For sure, but we cannot make, as we have been seeing these days, we cannot make a trade-off. Okay, today I just killed 2 pedestrians, I'm doing better than yesterday. No, it's not. I cannot compromise on that. To make sure of that, I am moving the system almost from a stochastic, statistical system to making so many tests, so many millions of hours of exercises, twins, that I am almost taking the system into a deterministic world. And that's the way they have solved it. Don't forget, the real problems remain unsolved. Mm-hmm. So we just will concentrate on our view on how could we solve such a difficult problem, the way in the future. Okay, let's say gaps are still open and difficult. I like this one. The European Union Act would not even tell you what does meaningful mean. They're not talking about real-time systems, real critical, real-world effect systems. They're talking about protecting our child, so protecting our privacy. Mm-hmm. We have gone to these real-world effects. We are considering sending missiles, buying millions of euros. Mm-hmm. So these mechanisms to control and to give the human the power assumes that we will be able to reduce such a difficult problem into a very, very narrow, very, very specific, forgetting everything else and just concentrate on one task. Think of a general or the captain of a ship. We will forget about the engines, we will forget about the crew. We will just focus on, I am being attacked by a drone, or I need to understand what's happening in the battle, where my enemies are. Just forget about everything else and just concentrate on that. But again, to do that, we must put in place all the mechanisms you've been saying and you will be talking about, all this planability, causality, full of hidden confounders, full of out of the design system. It's a full problem, and the answer must be a systems answer. We must put all these in place, and that's our solution, and that's the view we are given to the problem. I think that's it.
Okay, thank you very much. I was discussing with them. My question is stop it. Okay, thank you. It's about the final process to take decision in the human oversight. In what case or how do you consider finally we need an human on the loop to take decision? How do you consider the action of the, well, human on the loop or human in the loop, depending, financial, we were discussing yesterday. How do you consider, when do you decide or you consider that you must introduce the human in the loop in this approach, or to maintain the human on the loop with any kind of safety inspection model to receive the alerts about the action of the agents? How do you decide to do that? Please.
So the way we thought about it is that if we're addressing critical systems, and as Ignacio mentioned, something of high scale, like a missile, like something in the healthcare or in the financial industry, we would like to have human in the loop, always aware of the situation. And one of the things that we thought about is have, since we're processing a lot of data, have a task summarization component within our solution where all of this is being summarized into a UI or an interface where the human can get the summary of what's going on, and from there can make a rational decision on whether to proceed or not. Ignacio, yeah, you wanna carry over?
Okay, it's clear.
Yes, a critical point we understood was we are facing a real world problem, so we would like it to be deterministic. If we get into an airplane, we would like a human pilot on it. But if we need to use artificial intelligence, we would either take all the control mechanisms or test it as much as possible to try to approximate this determinism. That would be the equilibrium. Mm-hmm. Okay. Thank you.
Thank you.
Thank you.
Group number 5, please.
Vale.
Okay, so group number 5 is presenting their topic, causality and decision support in generative AI. So,
Okay. We will wait, no problem. Okay, so hello everyone, I'm Mario.
And I'm Javier.
And we're presenting the topic causality and decision support in generative AI. But before beginning, I must say something. I am really enjoying the summer school. And one of the things that I am taking away from this summer school is that I just met Javier. Javier, are you enjoying Granada so far?
Oh, thank you for asking, Mario. Yeah, Granada has been great. You know, La Alhambra, the summer school, La Chupeteria. Well, I've been really interested in the topic of causality.
Oh, really?
Yes, and I've been talking to people from ADIA, and they are applying it to real-world scenarios.
Oh, what are they doing with causality there?
Well, they are modeling macroeconomic problems, you know, these high-risk scenarios in which causality and association cannot be mixed up. And yes, so they are trying to model that without with structural breaks.
Okay, so structural breaks, that's thing that where the process changes and your model doesn't no longer work.
Yes.
But you know, there's something that struck me. When I was learning about causality, it turns out that causal theory actually do not contemplate the fact that a structural break can happen.
Why? Why does it that happen?
Well, if it's happening, it's likely because they're running an algorithm with certain assumptions, and they are not fulfilling that assumptions. One of the most common ones is the latent confounder. You cannot have a variable that you not observe that affects your whole system. So if suddenly a certain president states this is going to destroy a whole civilization, that affects the market, but you are not taking that into account.
So, Mario, what you're saying is that the problem is that we are not observing the whole system.
That's it. We only have a partial view of the whole world. But you know, we are in the agentic summer school, so I have an idea. And agents can be your solution for this.
Okay, Mario, what did you come up with?
Okay, so hear me this. You have this market panic, this thing that Donald Trump suddenly is making into the system. You cannot observe it, but it has traces over the internet, in news, in reports for government, in social media. This is all there. So what we can do is we can take an agent, scrap everything, and create a sentiment proxy for all this market panic. But you know, every time people have tried to input sentiment analysis into a causal graph, actually, they only produce a scalar. Does it make sense to summarize the whole expectation on the market in only one number for a given country? I think not. So we decided to move on and produce a proxy, or a vector proxy. We can have expectations about inflation, expectations about their employment, about growth, and about uncertainty.
Okay, so I see now when a politician gives some bad news about something, then we would take that into account and there would be no structural break, right?
Exactly.
But I'm concerned that these values extracted are not auditable.
That's the thing. We are in finance. This is a high-risk scenario. And so we have to, this system is to be auditable. That's why we can add an audit trail to all this data. And this means that the provenance, every decision by the system, every output in this vector is going to be accompanied with metadata, with the recent trace of the agent, and also with the original documents when this was extracted. This is important and also will allow people to understand why the solution and override them if necessary.
Okay, but Mario, we know that the statistical methods to learn the graph, the causal graph, are very expensive to run. So adding all this information wouldn't be a problem or make things more complicated?
Well, that's true. That's true that adding a lot of nodes is going to make everything more expensive, but agents can still help us here. Turns out that agents are really bad at stating causality. If you give them raw data, they give you bullshit. But they are really good at reasoning about domain knowledge, and we can exploit that. So take into account, for example, we have a candidate graph, a graph where all of this could happen. We don't know yet which edges are the correct or not, but all of this could happen. And only by looking at the semantics of the variable names, we already can know what could be. For example, the leading factor is not going to affect, it's going to likely affect the lagging factor, but the lagging is not going to affect the leading. So what we can do is we can have an agent committee, each agent with a different perspective, and try to filter which edges doesn't make sense. This way, we have already a really smaller search space, actually exponentially smaller, and also it will make more sense semantically for an expert.
I see, and also I think that we could also add human oversight to this by just seeing what the committee is voting and seeing in which points they are not agree. So what do you think about that?
That's actually, it's not only that we can, it's that we must. This is, again, high risk, and every decision should be passed by a human. A human in the loop is going to check which relationships that the agents propose are likely or not, and is going to have the final decision for the system.
Okay, that's a clever idea. I have a final concern, Mario.
What?
You know, even though we live in a global world, we have different cultures, and different news can affect differently to the models. So how does this take into account?
That's true. Turns out that data strategy for natural language processing is likely to be really noisy. but we can do something. We are working with macroeconomic data, and the nature itself of this data is that it can be split into countries. This means that we have what is called a multi-environment problem, which is a perfect suite for causal representational learning, which works on invariant mechanisms. What does this mean? We could add a new variable, which is the country, and this variable is going to absorb every behavior that is country-specific. That means the yellow node here will model stuff that only depends on Spain, or only depends in Japan, or only in Germany. And suddenly the rest part of the graph is going to have a mechanism that is stable all over the countries. This way, we are detaching the part that is dependent from the culture or dependent from a given country. For example, we know that in Spain we could be more pessimistic in the news than in Japan, and the green part is going to be causal and stable all across countries.
Oh, that makes a lot of sense. And yeah, using the heterogeneity of the data to create new structures, I think it's a good idea. I think the people from ADIA are going to like it, because it's going to make the models more robust, and also they will have fewer structural breaks.
That's it. And also a really important point here is that we are working within the same assumptions they are already having. So this is a drop-in replacement for what they have, and it's likely to save quite a millions of euros. And that's it. You are going to have few structural breaks because you have considered a bigger part of the model that was unexpected. Also, you are having more precise causal graphs. Also because now we're considering semantic information that was not considered previously only because they were only using statistical algorithms. Now we are also using the semantics at the scale with agents. And also, of course, next time Donald Trump puts a tweet, this model will have the consequence for this. Thank you very much.
Venga, animaros.
Okay, very nice presentation, very original, by the way. And well, my question would be, in order sometimes jump into real world scenarios is not that easy. How would you implement your first steps in order to, have a productive causal system, as you explained, based on agentic AI?
I think that the first step and the one that they are going to get the most benefit from is the phase one, which is actually starting to consider semantic data. This is going to be, actually quite tricky because you need to select which sources, like this will be, for example, which newspaper are you picking for each country, which reports are you taking into account, and also more important is if you are considering the vector, the variables that are being modeled, the number of scalars, the scalars that you see there, needs to be designed by an expert. An expert is going to see, okay, which expectations are actually relevant. So selecting which part of the world are you starting to see, this is going to be a process that is not automatic. You need to work with an expert, but later on you're going to have a huge benefit. So, and I think this is what actually is going to solve the problem of suddenly Donald Trump starting a war. This is actually changing the market, but because it's inducing a lot of fear, and it's something that you are not considering that could happen. And by introducing this into the system, suddenly you are fulfilling an assumption that you were not fulfilling yet. So this will need a lot of engineering with a real person who works on financial data and joint progress. But I think that starting this, you should start already seeing the benefits. The next two steps are more like fishing for efficiency, for a cleaner graph, and also more consistency. But we should start with phase one, and I think it should be instant benefits for them.
Okay, thank you so much. Thank you.
So, group number 6 is presenting their work in RAG and contextualization. So, when you want.
Good morning. I'm David. Together with Deraouf and John, we are going to present the proposal for the group number 6. Our proposal is contestable contextualization. As the subtitle says, RAG decisions are often unappealable. When an AI system triggers or makes a decision, the user usually don't have a way to challenge it. We think that's a problem, especially in a high-risk domain. So let me start with the sentence that drives this proposal. The problem is not the absence of transparency, it's the absence of a procedure to challenge, for a challenge. At first, we have the conceptual case when with the explainability tells you why. It gives you an explanation about the maybe the decision or how the system is using the information, but contestability on the other hand lets you act. It lets the user start a procedure to challenge the decision, not only being able to see the sources where they're retrieved, it triggers a response. Maybe it triggers a review, a correction, or just escalate the problem. The legal, well, we base this proposal also on a legal base, which is for example, in the GDPR, article number 22, if I'm not mistaken, it tells that the user should be granted the option to contest an automated decision. Also, in the AI EU Act, it talks about the human oversight. In a high-risk scenario, there should be, it's not an option that the system is not supervised by a human. So let me define the contestability. What it means is the ability of an affected user to challenge or trigger, not only provide feedback to the system, it's just be able to detect the step where the system is wrong, maybe the retrieval of the RAG system, and be able to record a documented response, not only to try to fix the decision or the response, also to justify the objection. We identify 4 points where the users are not used to be able to challenge the response on AI systems. First, the inclusion. Why was this source retrieved? It's usual that nowadays the RAG systems show the sources, they can cite the work and all that, but that's only transparency. You can tell the system that they were wrong in just that step, and you can record that. Second, the exclusion. You also don't have the ability to check what source was excluded from the set that they retrieved. Third, the interpretation. Why does that source support the claim? Maybe the citation is correct, but the source is correct, but the use is still wrong. And fourth, the action. Why did the agent act on the evidence? In an agentic system, every mistake it's passed to the next the next step on the decision. So even a wrong step can be a bigger problem in the future.
Yeah, so we always, like an example, make things easy. So what's, as the medical views, we have a decision-making system, which we need safety, we need privacy, we need everything should be correct in a way that we can see what is the error. So in a medical, in a system, like a decision system in the medical, we have the doctor and we have doctor and patient, and the relation between them. The doctor can have access to data to the patient, and then he need to make the workflow of the treatment. In a way, any decision-making system in the medical, we have the data or the history of that patient, and we have like then a doctor in the human process, let's say, don't talk about the autonomous or the agentic systems. The doctor should see the data of the patient, and based on this data, he can make a decision. Is there anything? What is the treatment plan? What we should do? Now, how we can integrate the AI in this process, and what is the best, maybe the best path, or that we need to apply? As like our maybe proposal that it can be, we have here in the medical infrastructure we have a lot of like many ready things, which is DICOM format. Anyone can know the DICOM format, which is like in any hospital international there is a norm about data, how data it's, let's say, the format of the data. So here we are presenting like, let's say, a robust representation based on graph, and then in a RAG system in a medical there is a retrieval. So how we can make the system like we can access what is the data that the retrieval gets. This is very important in medical, and as David explained. So the retrieval should tell us what is the data in this graph and what is the linking. So we think that the graph representation will enhance the retrieval system in the medical. And yeah, and always we are saying we should the human in the loop, but how is the question? How we can make the human in the loop, and how we can make privacy enhanced drug system? Because in the medical, privacy like trade-off with efficiency, because maybe if you want to good outcome, maybe you need to give more data about you, what you eat, how you spend your day. So the efficiency, it's about the accessibility of your data. So here it's like efficiency and data accessibility trade-off. So what we are saying here, it's like we need to present a context, maybe aware graph representation, then let's say multi-retrieval with a confidence map, because I will tell you, for example, in who is the winner of the World Cup in 2010, and it will say Italy, but it's Spain. So if any system gets the information from the official website of the FIFA, the confidence is very high. So we need to rank the confidence map based on the official, let's say, the official and the officials, like, so we need to give, let's say, a weight mapping, confidence mapping to our database. This is so there is, then later on, this data, it should be dynamic. So there is a doctor prescription, there is the agent prescription, and we need to map the data in order to have. Now, how we can make this appealing? Maybe we think that the system, we should later on adjust this confidence map based on the feedback of the doctor. So each time we need to like give like less confidence or more confidence to this data, and yeah, exactly. Sorry.
Okay, just in some questions we wanted to give like some summary in the last seconds. So we discussed a lot. We wanted to show like how we got to all this debate and discussion. We discussed a lot based on like some open questions we made, and yeah, we discussed about how to improve like first part of how to make information available to the stakeholders so that they can challenge the decisions. But we discussed these 3 topics, but we also found that there are some more open questions, which are, like, for example, what can we actually do after? What can we actually do after the decision is challenged? Okay, and we should try to think about it like in the different layers of the system. So we encourage all researchers here into trying to answer those which we found more difficult questions on how can we, once the contest is given or the answer is challenged, how can we modify and how should we inform also the stakeholders. So that was all. Sorry for the time we passed, and thank you so much.
Thanks for the presentation. I just have a very general question. So we're focusing on the title on RAG, and of course all the presentation is pretty linked to the RAG with the justification of the decisions and so on. But my general question is that if contestability is directly linked to RAG, or the concept can be extended to other kind of answers provided by an LLM that don't directly come from a database of facts or documents or issues.
We mainly focused on the RAG part because our topic was RAG, but it is extensible to general LLMs. The topic of contestability is not really explored in the RAG, about RAGs, but for example, with explainability, together with explainability, there's more literature about that. So it's kind of usable on all the and everything about LLMs.
Something I think I found interesting about this, and specifically like with RAG systems, is that as for me, for example, I used to see data representation and the retrieval part as some kind of backend related things, related with the developers, right? It's like our work. But this puts the spotlight on how also the users of the systems should somehow guide on some modifications in the systems, and that also poses like new questions about like, should we inform or how should we care about privacy when we model the system or we put like more filters or whatever in different steps. And if it were like just a straightforward pipeline with no RAG, we only can play, let's say, with a part of the model. So I think that's a tiny difference.
Thank you so much.
Group number 2, please.
Now is the team 2. After the team 2, we have a break for a coffee, 30 minutes.
Okay, so now we are having the second group, which is also talking about it's also the second group talking about the explainability topic. Okay, so.
Good morning, everyone. This is Group 2. I'm Kelvin Alfonso, and these are the members of our group. We were tackling the topic on explainability challenge in agentic AI system. So the first thing that we actually did was to go through the literature that we were actually given. And in one of the literatures, we actually able to identify a gap, which is LLMs are not perfect in explaining other LLMs or any other multi-agent. Then, within the other literature, we were also able to actually identify a discussion on minimum explanation package, which puts into consideration the life cycle of the agentic system. And with this minimum explanation package, it actually puts into consideration the planning, the sources, and also, and also the policy in fairness. Now, with this minimum explanation package, you are able to actually conclude that for an agentic system, it's very difficult to more or less explain everything. But what we need to do is to focus on one area. Now, we went back to what we have been doing throughout the whole of these 2 weeks, and to sum it up in one of the presentation, in this case, we were able to see the symbol emergency problem. We don't have the sun in these symbols, but now it becomes difficult for the system to be able to identify the sun. So in this case, what we want to focus is, because the question could be, is it the sun? Or could I be hallucinating because of this and this?
Okay, Kelvin, this sounds very nice, but how will it work? Let's put an example to make it easier to understand. So let's say that we have an agentic system that is an expert on radiology for cranioencephalic issues. And suddenly a dentist says, okay, I want to ask this agent, but wait, it's out of the domain, right? Because he was an expert on radiology, but so we want the agent, okay, it will give an answer, but we want the agent to say, hey, I could be hallucinating, and the reasons are X, Y, and Z. And the thing is to not rely on self-explainability. And for example, one of the explanations that it could say is, I could be hallucinating because I'm taking the information from this specific paper that is not related with the topic, and this with a counterfactual explanation. Also, it could say, I'm out of the taxonomy, so I could be making a mistake, or even by computing a distance in the embedding space, it could tell, okay, I could be also making a mistake here. But wait a second, how does this truly work? We have the agentic system. An agentic system is just a bunch of agents with access to some tools and some controllers. And actually, in the literature, they suggest that usually if you want to have explainability in agentic systems, it's very good to have a knowledge domain for every specific agent. So with that, you kind of know what are the frontiers of the knowledge of each agent. Then all of the different agents with their specific knowledge domain will interact. And here is where our solution comes. Here we have a very messy diagram, but let's make it simpler. So we want to say first, could it be a mistake? And then try to explain the potential source of the uncertainty. In order to do that, first we have the agentic system with the knowledge domain, as we already said. Then we have the agentic system with the result and the knowledge domain, and we want to compute a distance. We want to have a threshold that says, okay, this could be a possible hallucination. Good thing is the literature already tells us kind of how to measure these kind of things in the embedding space. And then, and one of the key parts is the counterfactual explanation. So now, when we have the uncertainty, we surpass the specific threshold, we want to provide an explanation. And with counterfactual, we can repeat the experiment several times, and let's take out the paper that we were saying that was out of scope. Let's take out a specific tool that could be the cause of the hallucination. And with that, we try to provide an explanation to the human, and then the human can provide the feedback to re-put the threshold that we were talking about and retrain the model with a reinforcement learning loop. And okay, this sounds very good, but what does the literature says about all of this? We have good news, that the literature already says how to compute distances in the embedding space in order to see the different hallucinations. It also says how important it is to have the knowledge domain in order to provide explanations. It also talks about contrafactual explanation. All of this is not new for all of you guys. You have already been in the summer school. And also it says how important is the human in the loop to prevent, okay, I could be hallucinating, let's stop here. Let's see how to recalculate the route and how to take advantage of all of this. So what's the new thing? The new thing and our proposal is putting all of this together. So thank you very much for attending.
All right, fantastic. Thank you very much for the presentation. So I'm going to go with a very quick one. Not sure if easy or not. How are you going to measure success?
Measure success. Okay. I believe that here the human in the loop is crucial. So first, you say at the agentic system, this could be an hallucination, but it's not a certainty. This is an hallucination. It's difficult to measure. So first, you suggest this could be a possible hallucination, and you provide feasible explanation with the contrafactual thing. So it could be because of we are taking the reason from this paper, we're taking the reason from this distance in the embedding space, and then the human is the one that says, okay, it was an hallucination. This paper has anything to do about the context, so in fact, you were making one mistake. Or, in the other hand, you could not be making a mistake, and then the human will say, you're not making a mistake. Don't tell me that this is a mistake.
But I was wondering more like, how do you, in the end, sell your product, right? So if this was to be like a funnel product, and I want to say, and now with this, you're going to reduce by this percentage my hallucinations, and then it's a little bit safer by this amount. How will you go about that, if possible at all?
Yeah, our main goal is to prevent the hallucination before it happens. So in the process of training, that was our main focus. The key thing is to train the model to be as precise as possible, to not be preventing all the time that this could be an hallucination. And with that, our main goal is to reduce by far many hallucinations, and overall to make the human accountable of what's really happening. So before something wrong could happen in an agentic system, everyone knows that when you use agents, sometimes it's go around and say and do things that you don't want it to do. We want to prevent that, and with that, reduce a lot of the hallucinations.
Thank you very much.
Thank you.
So, group 7 is ready? Group 7 is presenting their work about reasoning evaluations in LLMs and AI agents. So, when you want.
Good morning, I'm Carmen. Next to me is Matthew. And with Jorge, Joaquin, and Abdullah, we've been working on reasoning evaluation in LLMs and AI agents. Let me start asking you a question. Can we trust what AI agents do, and most important, why they do it? Before we give you our answer, let me guide you through the journey that got us there. What does it even mean to reason correctly? Why that question completely breaks when agents get into the picture? And how does responsible AI governance look like when the explanation you're evaluating might be a lie? And what's most crucial, what could actually do about it? Let's start from the beginning. What does it mean to reason correctly? So it's a simple question, but the truth is that the field can agree on an answer. And that disagreement is itself the first problem. So some say reasoning is valid when each step follows logically from the previous. Fine, but valid steps can reach wrong conclusions. Others say reasoning is sound if the final answer is correct. This is what most benchmark capture. But think about that for a moment. Couldn't we reach right answers because of entirely wrong reasons? Is that reasoning? And finally, we have faithfulness, which is did the trace the model give casually produce the output? This is the hardest to measure and the most important one for safety, because if we are evaluating some explanation that is not what the model actually did, we are reading a story, not auditing reasoning. So most benchmarks focus on soundness, and faithfulness remains an open problem, especially in agentic settings. Let's talk about numbers. 82% step-level accuracy sounds pretty good, right? But think about it as a 10-step reasoning chain, and you would get just 14% of fully correct chains, which means that 86% of the time, something went wrong along the way, and the agent kept going. And what should worry you the most is that 69% of smaller models produce correct answers, while reasoning wrong to get to them. So this is not a performance gap. This is a structural gap. So an example: we have an agent managing a patient. It detects drugs interaction, reasons under uncertainty, and sends an alert to a doctor. So that action is irreversible, because by the time we want to evaluate if the reasoning was correct to produce that alert, the action has already happened, and the doctor is already acting based on it. So in static LLMs, wrong reasoning or wrong answer are just wrong answer. You can correct them. In an agent, that's not the case. So this is why pre-action reasoning verification is not an academic exercise, it's a safety requirement. To think better why this keeps happening, we have to go deeper. In static LLMs, the world is simple. The model reasons, concludes, gives an answer, and when you have the full trace, you can evaluate it. In agents, that's not the case, because the action and the reasoning happens in the same loop. So as we've seen, by the time you try to evaluate it, the action has already happened. So this is not a performance gap, it's a structural incompatibility. And this is not just our observation. Lee and Hockenberger in 2025 surveyed roughly 60 evaluation methods, and every single one assumed that you have the full trace because consequences occur. What they don't do is distinguish between reversible and irreversible actions. So reversibility is not taken into account in evaluation frameworks. So the field has built excellent tools for a world where evaluation can wait. In agentic AI, it cannot.
Thank you, Carmen. In fact, not only are the current evaluation systems relying on unrealistic assumptions, but it's just not suitable for the legislation, because the EU AI Act, Article 14, states that human systems, we should have like human oversight in the AI systems, transparency on decision process, traceability, and ability to intervene and correct. But if we just rely on evaluation of the reasoning trace, well, that trace can be unfaithful, which it would look plausible, like from a high level, it's a plausible story, but it doesn't tell us the causal process. It's just what the model said. And overall, if it's unfaithful, the whole evaluation becomes a theater, which is why we believe that the textual trace must just become supplementary evidence, not at all the primary evaluation and control layer. So this is our proposal. We propose to evaluate the reasoning in agent systems before the action fires through this three-component system. So first, we will rely on entropy and self-consistency to derive an uncertainty score, which tells us which evaluates directly the reasoning. Following which we have a reversibility classification. So we'll classify each action depending on how reversible it is. And combining this with the uncertainty score, then the human can decide whether to proceed or not. And the last component is to log all the world states. So instead of just logging the reasoning trace, we will log all our signals, so the entropy, the uncertainty, the self-consistency matrix, and the uncertainty score. So we propose to evaluate before firing the action. Now I will detail each of these three components. So the first one is building this uncertainty score. For this, we rely on two very famous ways to analyze and evaluate LLMs. The first one is the token level entropy. So you know when LLMs are generating the next word, they output this probability distribution on what they think the next token will be. And they can be very confident, like say, 80%, they put 80% of the probability mass on this token, which means they are very confident about it and there is very low entropy. Or on the other hand, they can hesitate between multiple next tokens, meaning there are multiple branches they can take to decode the output sequence, and in that case, this is a very high entropy. So we propose to branch the decoding process at these tokens where there is very high entropy. And we combine this with, this time, the sequence level property, which is the self-consistency. So after decoding several sequences, we check whether how much they agree with each other to measure how consistent the model is and if the whole reasoning makes sense. So we aggregate this self-consistency outputs in different ways. So we can take the mean consistency or check whether there is one decoded branch which doesn't agree with all the others. We also split them. We check if they actually branch into incompatible groups. Check how much different actions, the different final actions they recommend, and also check whether they explicitly contradict each other. So we aggregate all these self-consistency outputs into this 5 matrix, and also take the overall sequence entropy H metric. So that will give us our uncertainty score. So that's component number 2. So we aggregate these entropy and self-consistency into the uncertainty. So for this, we take the Choquet integral, which is very practical because it models non-additivity. And in this case, risk is non-additive, right? So we think it's worse to have a lot of risk, a lot of decision divergence, and also a lot of uncertainty rather than each of them taken alone. So now that we have this uncertainty score, it's very easy to combine it with the human layer. So basically, we can take thresholds like if the risk is very low, then the human can proceed or not. On top of this, we also classify the actions as reversible or irreversible. So for instance, if the risk is medium and the action is reversible, then the system will flag to the human, okay, do you want to continue or not? But if the action is irreversible and the risk is medium, in that case, we will halt the LLM agent. And if it's very high risk, in both cases, the system should also halt the next action. Finally, the third component is to log everything, the whole state. So instead of the classical evaluation framework where you just log the reasoning traces, which, as we explained, they can be unfaithful and don't really represent what the reasoning tried to achieve, we would log everything. So the entropy at the sequence level, all the self-consistency metrics, the overall uncertainty at every single token, as well as the recommendation on the action to take for the human user. So that gives us a much better overview of the of the overall reasoning from the LLM system. So to conclude, our proposal fills 4 gaps in the field. So the first one was that there was no evaluation before the action. We propose to evaluate before LLM agent takes action. We also propose a world state audit log, which is much better than just the trace-based audit. We propose to classify actions, whether they are reversible or not, and combine this with uncertainty. And lastly, using Choquet integral captures non-additive interactions between metrics, which models risk much better. Thank you.
Thank you so much. So I liked your presentation, so you identified pretty well the problem. Of course, this is a preliminary proposal, as all of them, but I would like to get into the real-world adaptation. So I wonder if it would be able to deal with the time consuming on a real-time environment, dealing with the aggregation for each token, computing the 6 measures, applying the Choquette integral. I've worked with the Choquette integral. I agree it's one of the best aggregation operators. But do you think it would be so much time consuming to integrate it in a normal loop of interaction with an agentic system? Within the agentic system, I don't mean with the human in the loop.
I think Thanks. So yeah, that's a great question. So that's definitely one of the limitations of this work is that it would like add some latency into the system to compute all of these metrics. So it depends on how time critical the task under action is. But for for something like high frequency trading decisions, that's definitely not applicable. But for like more slow paced systems, the sexual latency is totally manageable. So totally different, depending on the use case. But if it needs to be cut down to like seconds, making the whole system decide within like the next 1 second, definitely this kind of machinery on the evaluation of reasoning will be very, very complicated unless we have very dedicated hardware. Yeah.
Thank you.
Okay, so finally, last group, group number 4, please. Yes, that's to the next slide. Okay, so finally, group number 4 is going to explain their work about governance of agentic AI in real organizations. So,
thank you everyone. Good morning, everyone. Thank you for allowing us to present. My name is Said Al-Khouri and Ghanem Al-Mazroui will be presenting on behalf of Group 4. And our topic goes around building a governance framework for agentic AIs in real organizations. As we know, AI moves from simply supporting decisions to now enabling and executing. And the question is no longer what AI can do, but also how does the organization remain in control. We are going to take you through three failures, 4 solutions, and why this matters now. So we start with the 3 failures. Each happened with a large, well-funded, and structured organization. Starting with Anthropic. Anthropic, during some of their simulations and the data pipeline, it downloaded over 7 million unauthorized or 7 million books without the copyrights. This had led the authors to raise a complaint or sue the company. 500,000 books were covered to the market on a cost of $3,000 per book, leading to almost a compensation of $1.5 billion, the largest copyright compensation in history. The lesson was there was no human verification layer over there. Moving to Air Canada's chatbot, a client wanted to go to his grandma's funeral. He wanted to book a flight he asked the chatbot several questions. It gave answers that contradicted the company's policies regarding the discounts. He sued the company, It was a small compensation, 800 Canadian dollars at most. However, the reputational damage was huge. And the lesson was there was no accountability boundary. Air Canada denied and mentioned the AI does it on its own and it's not our legal entity. Third, 2 Sigma, which is an investment fund. 2 Sigma had some internal problems internally raised in 2019. Those internal issues were not fixed for 4 years. Someone changed the parameter of 14 live trading systems without anyone checking or going through a 4-eye check. This led the SEC to fine them with $90 million. On top of that, they recompensated their clients with $165 million. 3 different sectors, in all within several years, with the same 4 problems. And we identified them as we see over here. Number 1, the warnings were there, but they were ignored. Anthropic's team knew where the data came from. 2 Sigma had internal reports of the issues since 2019. And Air Canada's website contradicted what the chatbot was saying. Number 2, there was no way to stop the system once it started, or the issue started. There was no kill switch, no rollback. On top of that, the damage kept building, it was accumulative. Number 3, there was no accountability. When something went wrong, no one knew who was responsible, and the organization pointed somewhere else, like Air Canada. Number 4, the tools the AI used were never treated as a risk until they became one. The paradox is over here is that these companies had risk policies. However, what they didn't have was governance built for agentic AI that acts on its own. And that's what we are proposing. Our topic defines 7 questions. Number 1, what can it do regarding deploying any agentic AI? What can it do? What could go wrong? Who is responsible if something goes wrong? How do we check if it's working? And what counts as acceptable to us? How do we make the principles real or operational? And how does the governance adapt over time, even if the system changes? Our framework answers all 7 within the 4 pillars. 4 pillars, each one designed to prevent one of the failures we just saw. Starting with the boundaries. What the agent is and isn't allowed to do. Moving to the roles and responsibilities. Named human, each with a clear job and a clear responsibility and assignment. Oversight, a monitoring layer that watches the agent in real time. And finally, mitigation, which is a plan if something goes wrong, who is going to pay for it. The first 2 pillars are set before the deployment, and the other 2 run the whole time the system is live. Together, they cover the full life of the system.
Thank you, Said. As described by Said, the 4 pillars spans the full system life cycle, and I'm gonna go through each one of them. So first of all, we have the boundaries and guardrails. This pillar answers the question of what the agent is and isn't allowed to do. How we force that, we have to define the frontier. We have a frontier of allowed actions that consists of 3 layers. First layer is the autonomous one. Those actions are the low risk, reversible actions and within scope. The next layer is the layer that requires human approvals. They are also actions which are reversible, but of a high risk. And lastly, we have the forbidden layer. Those consist of things such as external communication, reversible payments, and working with MNPIs. To force the action to stay within the allowed frontier, we have 4 control mechanisms. First, the agent can only use the tools that it needs, and each tool run in a contained environment. Next, anything that affects external party is gated by human approvals. And lastly, model parameters and configuration cannot be changed without an independent review. The second pillar is the runtime oversight. This is our monitoring framework. So it consists of three stages, and the order matters. The first stage is the working agent, where the agent performs the task, plans the action, and codes the tools. It emits a signal to the monitoring agent. The monitoring agent checks the runtime behavior for any policy compliance or drift and anomalies, and then it escalates that signal to the human in the loop. The human in the loop acts upon that signal, either to stop, approve, or deny the action. So why did we go with this design? First, humans cannot watch a fast-moving agent. There's too many operations, and it's inconceivable for a human to keep track of those things. Second, the agent fails in patterns that a human misses. It can be flagged as false positive, and the human dismisses that as well, it is a real issue. Lastly, humans must remain accountable. A human accountability cannot be delegated to an agent. Third pillar, and it's the most important one, it's the roles and responsibilities. So for every governance principle that we have, we assign the human name and a role to it. I'll give you some examples on those roles. For example, the first one is the agent operator. The responsibility is the day-to-day operation of that agent. Second, the system owner. It's the person who designed the agents and set the boundaries. Next, we have the independent risk reviewers, compliance, and internal audit. They work hand to hand. Lastly, we have the kill switch owner. It is the most important role in that pillar. It's someone who holds technical and organizational authority to stop the agent when in need. Fourth pillar is the risk mitigation and accountability. In this pillar, we determine the impact, we assign liability, and we plan a response. So step one, the impact assessment goes for every agent action. We classify it based on the following grid. For example, if it's a low blast radius action and it's reversible, then agent can work autonomously. While on the other hand, if it has a high impact and affects a lot of parties and it's irreversible, then it's held for human use only. Second, we ask who is liable. The deployer is always the liable, not the agent, not the vendor. The organization who put that agent in front of the board is the ones responsible for it. Third is the mitigation playbook. So for every risk class, there is a predefined response, and it goes with the following sequence. So first, we stop the agent, and then we escalate to a human reviewer. Then we roll back to the last known good state, and lastly, we notify all the affected parties. So the framework in action, as we can see, this is the life cycle view when each pillar gets activated during the life cycle. So for boundaries, they are set pre-deployment, and they are active during the runtime. As for roles, they are set from day one, and they span the entire life cycle. The monitoring is mostly active during the runtime and in post incidents. And lastly, mitigation, they span the entire life cycle. So as we can see, no pillar is sitting idle, and all of them together form a continuous loop that spans the entire life cycle. You can proceed.
So if we kept going, our question would be, can a monitoring agent itself, an AI, detect the three issues that happened with Anthropic, Air Canada, and Two Sigma? And if that's the case, that would be our case study to run our agent around. In the end, governance is not a document. It is the boundaries, the owners, the monitors, and the playbooks you can prove worked. And responsible AI isn't about slowing down the innovation. It is about building the governance and the trust and the control to scale it up safely. Thank you so much.
Thank you very much. Really, I enjoy listening to you. I enjoy the proposal. I would like. How are you thinking about to use in a special possible case study? The idea is to have a case study to analyze or to try to, particularly the guardrails, to define a guardrails and so on. I think it's a very interesting proposal, a very interesting model, and it's not really a question, it's a suggestion to think in a future, in a real application, to define the guardrails and to define the mechanism for checking the human on the loop, because with a real case study, really maybe a very interesting work. It's my suggestion.
Yeah, that's a great suggestion. If we have more time, we would like to put a proof of how the framework would act in real life scenarios. But in our case, it's we build the framework as like a theoretical proposal, and we hope that we have more time to test it on real life scenarios.
Thanks. Very good presentation.
Also, the suggestion was very nice, and actually something that we were discussing earlier while working on the project. Since we come from the operations at ADIA, and we work in the audit and the IT, and we have from real estate. So we were going to initiate the testings from our perspective, if we were allowed to test what we are doing with the AI in ADIA to implement this governance. Hopefully, maybe soon enough, this will be in a real case scenario within our organization. That's what we wish for.
Congratulations. Thanks.
Thank you so much.